Good morning, Madam Dr. Samahani binti Suradi, Senior Lecturer of UTHM and Lecturer of Fluid Mechanics. My name is Rukeshwan Kaliselvan from DAK. Today my group and I will be presenting test 2 which focuses on application of fluid mechanics in engineering system. I will begin with a brief introduction of the topic. Fluid mechanics plays an important role in many engineering applications such as community water piping networks and floating platforms. This system must be designed carefully to ensure efficient fluid flow, structural stability and public safety. Based on standard fluid mechanics theory, several key parameters influence system performance. These include head loss, shear stress, buoyant force, and stability. Understanding this principle helps engineers predict fluid behavior and design systems that are safe and reliable. In this presentation, we will first discuss the engineering responsibilities, followed by analysis of fluid flow concept, and finally the stability of floating bodies, supported with diagrams and sample calculation. With that, I will now proceed to next part of the presentation.
Assalamualaikum everyone, my name is Nur Ali Shazha. So today I will be presenting about engineering responsibilities. So let's go through it. So let me walk you through the key responsibilities, which is the first one is design a safety for long-term operation. So as you guys know, engineers must select the right materials, anticipate dynamic loads like wave or pressure surge, and apply safety factors. So for water system, this means specifying the correct pump type based on system curve and designing pressure zone with devices like pressure reducing valve or PRVs. For floating structures, it involves stability engineering, applying meta-centric height calculation to design hull forms and balance. From my slide, there's three key points, which is pump station engineering, pressure management, and water quality protection. For the first key point, which is pump station engineering, it mentions that specified pump times like centrifugal, positive displacement, power requirements, and control system based on system curve and operating points. For the second point, which is pressure management, design pressure zones and specify pressure reducing valve PRVs to maintain safe pressures throughout the network. The last key point for design and safety, which is water quality protection, ensure minimum flow velocities to prevent stagnation and bacterial growth. So there's also floating structures, which I just mentioned just now. There's three key points under floating structures, which is stability engineering. So it's apply meta-centric height GM calculation to design full forms, compartmentation, and ballast system, like just I mentioned before. The second key point is load management. So develop loading manuals and stability booklets for various operational conditions. And lastly is structural integration, which is coordinate stability requirements with structural design for wave loads and operational stress. Second key point under the engineering responsibilities is systemic risk assessment. So this is the key points that I have found, which is a water hammer analysis for the first one, which is moderate transient pressure from pump trips and valve operation using software like AFT Impulse or Bentley Hammer. For the second point is surge protection design, specify and size surge tanks, air vessels, vacuum breakers, and surge relief valve. So for the third key point, which is redundancy planning, where design backup system, emergency power, and fail-safe modes of operation. And lastly, for the engineering responsibilities is extreme event planning. So as we all know, currently the world is experiencing a lot of event, which is like especially flood. So as you guys can see here, it says account for earthquake, flood, storm surge, and maximum credible accidents. So that's it for engineering responsibilities.
Nice. This is application of fluid mechanics in floating platform stability. Okay, first, buoyant force. Have you ever wondered why hard floating platforms do not sink, even though they carry heavy loads? The answer lies in simple but powerful concept in fluid mechanics called buoyant force. Okay, buoyant force is explained by Archimedes' principle. It states that when an object is placed in fluid, it experiences an upward force equal to the weight of the fluid in displace. Mathematically, this is written as Fb equal to Pgv, where P is the fluid of density, G is gravitational acceleration, and V is the displaced volume. In engineering, this principle is very important. Floating platforms such as pontons and floating jetties remain stable when the buoyant force is equal or greater than their weight. If the buoyant force is too small, the structure will sink. Okay, in summarize, buoyant force is the key reason floating platforms stay afloat and stable. Understanding this principle help engineering design safe and efficient floating structures. Next part is stability of floating bodies. Okay, why don't floating platforms easily tips over? The answer is stability in fluid mechanics. The stability of a floating body depends on the center of gravity and the metacenter. A floating platform is stable when the metacentric height, which is Gm, is positive. The formula is Gm equal to Bm minus Bg. If Gm is greater than 0, the platform is stable. If Gm is 0, it is naturally stable. If Gm is negative, the platform becomes unstable and may overturn. Okay, I can conclude from information above. Therefore, a positive megacentric height help floating platforms return to their original position, ensuring safety and stability. So, metacenter obviously must positive. So, we want the platform is stable. Thank you.
Hello, my name is Derek and I'm going to present about analysis of head loss. There are two types of head loss, which is major head loss and a minor head loss. And I'm going to talk about the major head loss, where it caused by surface friction between two moving fluid and the pipe wall, where the laminar flow is less than 2000 and turbulent flow is more than 4000. The velocity head is where the head loss is proportional to the square of the velocity. Minor head loss, where it occurs when the local disturbances in flow, such as fittings, valves, bands in the piping section area. Loss coefficient, where dimensionless value for each compound, which is determined from the experiment. And the total head loss is equals to overall energy loss is equal to both major and minor loss. Next, I'm going to talk about the no slip condition. There are 7 no slip conditions. First is a fluid in direct contact with the solid to the surface due to viscous effect. Next, the fluid property responsible for the no slip condition is called viscosity. Next, important boundary condition in formulating initial boundary value. The next one is fluid flow usually confined by solid surfaces. Then it occurs on viscous liquids. It is a condition in which the liquid is equal to solid surfaces. And lastly, it produces zero velocity region. And lastly, I'm going to present about the shear stress. Fundamental concepts in fluid dynamics plays a crucial role in behavior of fluids in various engineering applications. Next, due to fluid viscosity and velocity gradient, the force exerted by a fluid on a surface parallel to surface. Next, I'm going to talk about the Newtonian fluid. The formula of Newtonian fluid is shear stress is equals to viscosity over du over dy. Next, predict flow regimes. Shear stress is used to predict the flow regime including laminar or turbulent flow. Next, calculate flow regimes. Shear stress is used to calculate fluid properties such as viscosity and density. And lastly, model complex fluid behavior, where shear stress is used to model complex fluid behavior including non-Newtonian fluids and multi-phase flows. Thank you.
This is sample calculation in head loss. So for example, a 50-meter long pipe with D equals to 0.05 meter carries water at 2 meter per second. Assume friction factor is 0.02. So use formula HF equal to FL per D times V square per 2G. So F is friction factor, L is pipe length, D is diameter, V is fluid velocity, HF is friction heat loss. So just substitute. So you get answer HF equals to 4.08 meter. So next, sample calculation shear stress in pipe flow. So water flow through a horizontal circle pipe. The dynamic viscosity of water is 1.0 times 10 power of negative 3. The velocity gradient near the pipe wall is 150 second per negative 1. Calculate the shear stress in pipe flow. So you just use formula T equals to dynamic viscosity du per dy. So du per dy is given already in question 150. So just substitute, you get the answer is 0.15 Pa. So unit is pressure Pa. So next, sample calculation beyond force. So a floating block displays 0.3 meter cube of water. Calculate beyond force. So you just use formula Fb equals to Pgv. So substitute, you will get the answer 2943 Newton. So next, sample calculation of stability of floating body. So unit used for this calculation formula is Gm equal to Bg minus Bg. So after you calculate the answer of megacentric value, so must be positive. If positive, it means stable is more than 0. For example, after I calculate this question, I get answer 0.0267. If so, I get more than 0, it means it's stable. If less than 0, it means it's unstable. If equal to 0, it means neutral. So this is concept calculation in stability of floating body.
So let's go through to everyone's favorite part, which is conclusion. So this presentation has demonstrated that the principles of fluid mechanics serve as the critical foundation for designing, analyzing, and operating both water piping system and floating structures. Through the application of Archimedes' principle, Bernoulli's equation, Darcy-Weisbach, friction loss, and metacentric stability analysis, we transform theoretical concept into safe, reliable, and efficient real-world infrastructure. The engineering responsibility lies in the selecting appropriate materials, anticipating dynamic loads, mitigating risks such as water hammer, and ensuring compliance with international standards, all to protect public safety, ensure system longevity, and support sustainable development. In essence, fluid mechanics provides the scientific language, and engineering applies the necessary judgment to create a system that function effectively in the service of society. That's it from me. Thank you very much.